Hello, everyone.
Sorry, I was just going to introduce you, Benedict. So our next speaker is Benedicte Colnet, who is now has her PhD, excellent, and she was working with Julie Josse and has now moved to the French Ministry of Health, working on their medical devices policies. Take it away, Benedict.
Thank you, Robin. Thank you. Hello, everyone, and thank you for being here in the evening in China. So I will talk today about how we can reweight randomized control trial for generalization. And as Robin said, so I did my PhD with Julie Josse and also Erwan Scornet and Gaël Borboco in France, in Paris, in RIA. And so the work I will present is from my PhD and done with my 3 PhD advisors. So we are in a causal inference conference, so you all know about randomized control trials, and maybe you don't know, but RCTs are quite old and we can find old RCTs. What is really new today is not the fact that we are doing a lot of randomized control trials, but also because this is the gold standard, and it has not always been the case. And you can see here a screenshot of the FDAs with a new treatment that has been allowed through RCTs. But let's say 20, 30 years ago, the scope of RCTs has been increasingly under scrutiny. For example, because of the short time frame, the limited sample size, or the unrealistic real-world compliance, or representativeness or lack of representativeness of the sample. And here I have underscored the representativity of the sample because I will focus the presentation on this aspect. What do I mean when I say that the sample is not representative? This is a real-world example with here a CRASH-3 sample. So the CRASH-3 is a randomized control trial, and the trauma base is a French cohort, and the datasets are about patients suffering from traumatic brain injuries. And the Glasgow score here is the severity of the trauma. The higher the score, the lower the severity of the trauma. And here I have just compared the two distributions of the two datasets. What you can see here is that the population that has been recruited in the CRASH-3 trial is not the same as the population in the trauma base. And for example, you can see that you have less severe or highly severe patient in the trauma base, whereas you have, let's say, mild and moderate case in the CRASH-3 trial. This is a problem when we want to infer and generalize or transport the causal effect measure on the CRASH-3 trial to another population. Why? Because we can say that most of the treatments are supposed to say heterogeneous. And when I say that treatment effects are heterogeneous, I want to say that depending on your character react different to the treatment. This is an hypothetical drawing where you can see here the Glasgow score, so our covariate, and here you can see the probability of death. And let's suppose that the true response when you are treated is in blue, not treated, sorry, is in blue, and depends on the Glasgow score. And you can have another response function when you get some treatment, here the tranexamic acid, and this treatment will lower your probability to die from the traumatic brain injury. Here, what you can see with this drawing is that people with this range of Glasgow score have a higher effect than people on the that have super high or very low Glasgow score. And here, what you would say is that probably if the response function is the following, then the CRASH-3 trial will overestimate the treatment effect you will observe in the trauma base. And my concern today is to use the two data sets to generalize the CRASH-3 effect to our target population here, the trauma base. If I want to put some notations about this problem of the data sets, I can use the potential outcome framework you probably all know about here. And what is different is the fact that I have two data sources. I have a date is the cross trial, so a trial of size n with some distribution and another sample of the target population with a size m. And the key aspect is that assume here my trial is sampled from a population PR, and my sample of the target population is sampled from another population P. Here, in my example, I don't need to have the response or the treatment allocation. I just need to have the covariate, like a sample of typical patient I will have in the French hospital, whereas here I have a trial that can be conducted in another country with some patient characteristics, treatment allocation A and response Y. Here it's continuous, but for the previous example, it can be binary, dead or not. So typically, when we only have a trial and when we want to estimate the average treatment effects, ATE, we can use, and if we are interested in the difference, the causal effect on the difference scale, we can use the Horvitz-Thompson estimator, HG. It can be other estimator, but assume we use one. If we use this estimator, and typically the probability to receive the treatment in the trial is 0.5, then this estimator is said to be unbiased and consistent. Yes, but it is to estimate the FR, that is the average of 1 minus Y0, which is different than the expected for target. And this is the key aspect. And here I only put some notations on the problem I described in the introduction. Intuitively, what we want to do is to reweight the trial's data so that the population looks like the target population of interest. So what we want to do is to reweight here with, for example, W, and W depends on the covariates, so that we are somehow reweighting the trial. So you can recognize here this of the IPW in causal inference, but here the S come from sampling weighting and has been introduced by Elizabeth Stewart and co-authors in 2010. What do we need? Because I just said I want to use some weights, and here the weights can be defined as the ratio of the target distribution PT and the randomized population distribution PR. And I need some causal assumption to identify my target population effect tau T from the trial and the observational sample. And these assumptions are very, very close to what you're used to in causal inference, but with some differences. The first one is usually called transportability assumption, is very close to the ignorability assumption in causal inference. Here, what I want to do is that condition to some covariates, here the treatment effect modifier covariates, then my distribution of Y1 minus Y0 is the same in the two populations. And another assumption is the fact that it is close to the overlap or so-called positivity assumption, is that I need that each individual in the target population can be represented in the trial. And I like to call it the support inclusion also, that is the support of the target distribution is included in the support of the randomized control trial distribution. And now I start with the research question we tried to solve. The idea is then we don't know the weights, and we have to learn the weights with our target sample population. So here now, my W is a W hat and depends on the two population, N the trial and M the target sample. And the question is, this estimator, it depends on two data sets, and I am wondering what are the properties of such procedure. Of course, ideally, I would like this estimator IPSW to be unbiased. And also, I am wondering how the variance is doing with two sample size. And this is the research question of interest. And before going into the research question and the results, I want to do a short focus on the state of the art. So reweighting can be found back in the early 20s. In fact, you can find, in fact, the idea of reweighting under the name standardization in epidemiological book. But what is new in this approach, like the approach proposed by Elizabeth Stewart, is the fact of using two samples and using an external representative sample to reweight the RCT. And today I will not talk about other estimation approaches that have been proposed to generalize a randomized controlled trial. I will just focus on reweighting. I will focus on open questions. As I said, what is the impact of the two data sources size? And also, which covariates should I use once I have enough covariates for identification? Is there a problem if I have more covariates? And for the rest of the work, I will do only one assumption, which is that I will assume that X, my set of covariates, is composed of categorical covariates only. Okay, back to our IPSW estimator. Here, I will focus on the oracle estimator to understand the properties of the estimator. Here, if I put a star, meaning that this is an oracle estimator, and I put T, R, and pi to say that this estimator knows the true probabilities PT, PR, and knows the true pi probability of getting the treatment in the trial. If I do so, it's quite easy to derive the finite sample properties and therefore large sample properties of this estimator. This estimator is unbiased and also has a finite sample variance that can be decomposed in two terms, this first term and the other term. You can remember V oracle, and I will come back to this V oracle later. But in practice, we don't have PT and PR. We have to estimate it. And I will start by estimating only PR. We saw with the trial data. So P hat R depends only on the size of the trial. And in fact, because categorical covariates are involved and only categorical covariates, then estimation is very intuitive and corresponds to how many times the specific combination of category X appears in the trial, just counting individuals. And here, this estimator, see here, I put only a T in the notation, meaning that this semi-oracle estimator knows about the target population, but not the randomized control population. And if I derive the properties of this estimator, first of all, I will observe that this estimator has a bias now. And this bias is positive but exponentially small and is due to the fact that we can have undercoverage of some categories in the trial. We can also bound the finite sample variance of this estimator, and we can also so this bound depends on VSO for semi-oracle variance. And in fact, VSO will correspond to the large sample variance. And what is very interesting is to find that, in fact, VSO, the large sample variance of this semi-oracle estimator, is smaller than the oracle estimator variance. And this is a very well-known result in causal inference where estimating the weight can be more efficient than having the true weights. And now, if I come to my completely estimated weight, so now I assume that I am fitting PT and PR, so I have P hat T and PRX, sorry. And so now my estimator only depends on N and M, and I don't know anything else except of pi. If I derive the properties of this estimator, I will find that this estimator has the same bias as the semi-oracle estimate. And now my variance has a bigger bound that depends on N and M. And I will find that this estimator will be consistent only if my two samples are converging toward infinity. And I really like this result because if we are looking into large sample properties of this estimator, in fact, the large sample variance depends on the regime we have. Do we have a super big observational data set compared to the trial? Or do we have somehow two data sets of roughly the same size? or a super big trial. For example, if m is way bigger than n, so lambda is going toward infinity, for example, you will find that this variance will be the variance of IPSW will be somehow constrained only by the trial n and not by the observational sample, which is intuitive. And here we will find only the VSO term, so the semi-oracle, because lambda is going toward infinity. And then you can also look at the problem if m equal n and so on. So in fact, the variance depends on the size of the two datasets. I will skip the slide, but put the slides on my website, but you can also wonder what if now I also estimate pi? Even if I know pi, I can estimate pi. And in fact, estimating this probability to get the treatment in the trial will give you a more efficient estimator. For the same reason than before, it can be sometimes better to estimate the weights than having the true weights. And this is a result I really like in causal inference. Because now for the last minutes of the talk, I want to focus on additional covariates. Now, we've proposed some result for large sample variance, but another problem in practice is to understand the impact of adding additional covariates. When I am talking about adding additional covariates, I am thinking about adding covariates that are not necessary to identify the effect. Remember, if I want to identify the treatment effect, I need to have both covariates being both treatment effect modifier and shifted. But in practice, we may want, and I've seen this with my collaborators, we are tempted to add as many covariates as possible to be sure to identify the effect. Of course, it does prevent to miss important covariates. But what happens if gender is added but is only shifted? That is, gender is typically here not needed for identification. But if we are hesitating, should we put it or not in our datasets? And here you can see that adding gender would be a very, very bad idea, because this would lead to inflate the variance of our estimator. Here, the plain lines are the theory, and the dotted lines are simulation. And here you can see that if I add a covariate, depending of PR and PT, if PR is very different than PT, then I can inflate my variance. And for example, I can inflate my variance by a factor of 3. So you really don't want to add gender in the datasets. The result we propose here is to say that the estimator with additional covariate V is equal to the variance of the estimator with only X times the ratio of the density PT PR of V. But in this work, we also worked on some covariates that can be for the better. What happens if a non-shifted covariate, so for example, gender now is not shifted, 50-50 in the two populations, but in fact, the reaction to the treatment is really dependent on gender. And now, if you do so, you would reduce the variance. And this is a simulation, a semi-synthetic simulation, where you see that the extended dataset in purple has a smaller variance than the estimator with the minimal covariate sets. I can derive here also the theory, and our result is the following. The variance with the additional covariate V is smaller than the variance with only the minimal set of covariate X. And here you can see what you gain when you add the covariate V. You will reduce the variance if the new covariate V is really, really explaining the variation in the treatment effect. So in our work and in the paper, we have a semi-synthetic simulation. So we use the real to build a response function and then do the simulation and illustrate all the results. And specifically here, if I focus on the covariate set, you can see that if I use the minimal set here, I can get the right ATE. then I can lower the variance estimator if I have all the treatment effect modifiers that are not shifted. But if I add covariates that are shifted and not modifying the treatment effect, I will increase the variance. We also have simulation to illustrate the fact that we may want to estimate the pi. So I really talked a little bit about this, but you can go in the paper to find the details. And now to let time for questions. Maybe I want to say that RCTs are and will remain cornerstones of modern-based medicine. But what I want to do in my research work on with usually Erwan and Gail is to say that maybe we can use real-world data to help and strengthen the clinical evidence. But if we want to do so, we need to understand the theoretical properties of such estimators. And so in this talk was one little step toward a better understanding of the estimators and methods that are currently proposed in our community. And here we try to focus on finite sample results because we do think that in practice we don't have large sample and we cannot always have validity of asymptotic results. And also we worked on covariate selection because we realized that in practice is a really important question. And here we showed that this is really, really important to choose covariates correctly. And I want to thank you for your attention and in the evening in China, and please ask any question you may have.
Thanks very much, Benedict. So I'll just kick off with a question. So presumably, when you talked about the fact that if you add in a variable which isn't an effect modifier but is shifted, it will increase your variance. And if you add in one that isn't a effect modifier but is shifted, sorry, is an effect modifier but is not shifted, then it will reduce your variance. So presumably there's some point in between, is there, where it is both an effect modifier and shifted, and is maybe not clear whether you should add it in or not? Have you sort of looked at this trade-off?
If we have like a treatment effect modifier that is shifted, but we are, you mean hesitating?
Yeah. So, I mean, have you characterized exactly what the trade-off is?
So in fact, so if we want in the end to be unbiased, and for identification, we in fact need to add all the covariates shifted and treatment effect modifier. This is why we did not focus into this in-between ratio. We were really thinking in the fact that, okay, I know, this is big assumption, what is the minimal set of covariates I need to adjust on. And then we only looked at covariates that were either shifted and maybe prognostic of the outcome, by the way, but not modulating the treatment effect on the scale we are looking the treatment effect, or the reverse that are only. But sorry, maybe I did not get exactly your question.
So I just, you sort of said the basically two categories. Either it modifies the treatment effect, in which case you should put it in, but it's not shifted, right? And that was what I understood. Or it's shifted and it's not a treatment effect modifier. So presumably there must be, a set of combinations of those things which would not change your variance, right? So it wouldn't neither benefit you or harm you to add them in.
Yeah, totally. No, I get your question. In fact, when a covariate is both treatment effect and shifted, I need to put the covariate because I need to have, it's for identification. But I agree, I could say, but indeed, there is an in-between. I agree with you, and we've not looked into this in-between thinking. But still, okay. I think that one of the main results we've talked about with our clinician collaborators is the fact that if you have a covariates that is really, really shifted and a lack of overlap in between two data sets, and you, because of previous trials, have good reason to think that this covariate is not modulating the treatment effect, we do recommend to not put this covariate. because in fact it can be very, we can be tempted to add all the very, very shifted covariates in the data set, like spontaneously, to be sure to miss nothing. And in fact, one of the results is to say, yes, but in fact, if it's not modulating treatment effect that much, you should not do this because you will, because of the variance inflation, you will probably not conclude about anything. This is somehow the main applied result we discussed with,
Okay.
Mm.